Today we are going to be covering section 12.3, one-sided limits and limits at infinity. So take the time to write the title, your cutout, and example number 1. At this point, all of you guys should have a Chromebook as well. You should log into desmos.com and see, once you written down the title, the glue your cutout, and wrote this down, see if you can graph this piecewise function. We've done piecewise functions before, so you need to be able to graph it and see what it looks like. Then we'll start. So go and pause it, and then we'll continue once everybody's ready. If by any chance I do not get a chance to finish these notes, because we do only have 45 minutes, you want to make sure that you log online, and I'll post them on Google Classroom this afternoon. Go and pause it, and we'll continue. Excellent. So let's go and see how you guys graphed it. We have desmos.com. The first one is f of x equals x plus 6, and we're going to restrict our domain to be x is less than 2. I'll leave this one for last, the second one. Let's go do the third one. The third one we know is a parabola, and we just gain a piece of it, so it'll be 1/2 x to the power of 2, and we're going to restrict our domain to x is greater than 2. So all the values that are x is greater than 2. Now, how did you guys graph the second one? So I know that if I type in f of x equals 2, I know that I have a horizontal line, and if I restrict my domain to x equals 2, notice that's no longer there. So therefore, I do have a problem. It's supposed to be is the green line, but once I place my restriction, it's gone. So is there any way that I can modify this so I can just graph what I need with this restriction here? So I'll let you guys think about it, and then we can try it out. So I'll give you guys 20 seconds to be able to decide, see if you can figure out how to make that show on your graph. 20 seconds. So talk to your partner. 10 more seconds. Okay, let's do 10 more seconds. Did you guys figure it out? Excellent. So therefore, how do you guys type it in? So I know that I have to type in that f of x equal to 2 as my function. So I just want that y value to be 2 when the x is 2. So therefore, that's only a point. And you guys have seen this before, where the point is flowing above or below. So that's the function. So we're going to copy that into your notes. I'm going to make a x and y axis. In this case, I'm just going to need probably just the first quadrant. So I'm going to make a graph. So we graphed this type of graphs before. So x equal to x plus 6. My y-intercept is 2, 4, 6. My slope is up 1 into the right 1. So let me do it with pencil so I can go back and erase. And I want to be able to limit when x is less than 2, so I'm going to stop right here. So I'll be from here all the way down. And it doesn't include the 2, so we're going to leave it as open, where it doesn't initially show on your graph, on Desmos. The second one is y is 2 when x is 2, so therefore that is a point. The third one is a parabola with your vertex at 0, 0. And I'm going to plug it in 1. Plugging in 1 gives you 1 squared is 1. Half of it is half. Plug in a 2. 2 squared is 4. Half of it is 2. Plug in a 3. 3 squared is 9. Half of 9 is 4.5. Plug in a 4. 4 squared is 16. Half of 16 is 8. Plug in a 5. 5 squared is 25. Half of 25 is 12.5. So I'll be around here. And I just want to restrict my values where x is greater than 2. So I just want this part of the graph. And it's curved. So that's what you should have for your graph. So let's go over the cutoff for today. One-sided limit. Limits that we have discussed so far are called two-sided limits. So the limits that we covered on section 12.1 were limits that reach the same point from the right and from the left. They reach the same y value. Today we are going to cover one-sided limit. One-sided limits involve x values only on one side of A. So either going to be on the right-hand limit or the left-hand limit. And notice the only difference that you'll see is the little plus after the A or after the number, or a little minus. The plus means that you're approaching it from the right, from the positive infinity, and the left means that you're approaching it from the left, from negative infinity. And you are approaching the value of A. And we read it as the limit of f of x as x approaches A from the right equals to L, in this case a number. Same thing for here. Now, if we actually just look at it graphically, so we're going to do it two ways. We're going to do it graphically, and we're going to do it algebraically afterwards. So graphically, if we go back to Desmos, I want to be able to find out what is the limit of f of x as x approaches 2 from the left. What does it approach? So let me switch over to Desmos. And if I approach it from the left, as x gets closer and closer to 0.4, as it gets closer and closer to 2, what does it approach? It's undefined, but it gets closer and closer to the y value is 7.96. It's going to be 8. So therefore, the limit, and you can see it from here, as it gets closer and closer to 2, the x value is going to be reaching 8. And we also need to find the right-hand side limit, the limit of f of x as x approaches 2, but now it's going to be from the right-hand side. So therefore, we are going to approach it from the right. So as we approach it from the right, what is going to be the y value? 4, 3.5, 3.1, 2.9, 2.5. It's undefined. It's actually a cover. So it's going to be approach 2. And on this must tell me undefined, but because of this point, we know it's going to be even 2. So therefore, the y value is going to be 2. And you want to make sure that you place a little arrow to indicate the left-hand limit. Now, algebraically, if we are going to do this algebraically, let's write down here the limit of f of x as x approaches 2 from the left. So if it's approaching 2 from the left, I need to decide which of those three pieces am I going to use. Correct. If it's from the left, I'm going to use this piece. So even if you can't graph it, you should be able to calculate your limit using the equation. So therefore, I'll be x plus 6, and we know that we can just plug, because this is a linear equation, we can just plug in a 2. So that'll give me 8. So the limit of f of x as x approaches 2 from the left is 8. And now we need to be able to do the same thing to find the limit of f of x as x approaches 2 from the right. I need to decide where do I need to plug in the 2. So from the right, we are going to use the other equation, which is from the right is going to be from here. We're going to use this equation, and we're going to plug in a 2. So therefore, it'll be 1/2, plug in a 2 square. That gives me 4, half of 4 is 2. So therefore, the limit of f of x as x approaches 2 from the right will be 2. And notice that we end up with the same answer, whether you do it graphically or algebraically. Example number 2. Go and copy it down and graph it on Desmos, and then we'll start. Go ahead and pause it, and we'll start as soon as it gets ready. Excellent. So in this case, if you type it on Desmos, we just have one function. The function is f of x equal to the square root of x. Now, one of the things that we do have to be careful, because in this case, this is not a full, it doesn't go from negative infinity to positive infinity. It starts at 0, 0 and continues over to the right. So let's go ahead and graph on our paper. No, that's not the buffer, yes. We still have plenty of time left to finish these notes. So first, I'm going to plug in a 0. If I plug in a 0, I end up with 0 square of 0, 0. I'm going to plug in a 1. Square of 1 is 1. What's the next number that I should plug in? Correct, a 4. 2, 3, 4. If I plug in a 4, the square of 4 is 2. The next number that I'll plug in is, say, 9. 5, 6, 7, 8, 9. The square of 9 is 3. So therefore, this is our graph. So we can do it algebraically or graphically. And on the homework, you have a choice of doing either one on some of the problems. So let's start with the first one. The limit of the square of x as x approaches 0 from the right. So as you approach 0, what is the value that it gets to? It gets closer and closer to 0. Or otherwise, we also know that algebraically, we just plug in a 0, it gives us 0. Now let's go and find the limit of the square of x as x approaches 0 from the left. So here's 0. From the left, there's no graph. So therefore, it does not exist. Because this graph does not have a 0. If it was any other point, if it was at 4, yeah, there'll be a limit from the right and from the left. But in this case, at 0, there's no such limit. Go and glue the next one. And example number 3. Go and pause it, and we'll continue once everybody's ready. Excellent. So therefore, you should have it cut out, glued. Now, before we actually get to example number 3, let's go over this. One-sided and two-sided limits. If the following limits exist and L is a real number, then the following is true. Now, you guys have seen this before, if and only if. What is the difference if we just say if and only if? Do you guys remember? Talk to your partner and see if you guys remember. What is the difference between just writing if or if and only if? And you guys have seen this in geometry. So I'll give you guys 20 seconds. Ten more seconds. So what did you guys decide? If it says if and only if, means that it works both ways. If the limit of f of x, which means that it's both sides, from the left and the right, if there's such a number, that means that there's a limit from the left, from the right, and from the left. And if there's a limit from the right and from the left, means that there's a limit from both sides. So it works one way and another. That's why whenever we use if and only if. And there's going to be times that sometimes they'll abbreviate it and they'll say if with double F. And some of you guys will think that's misspelled, which is not. If means if and only if. Now let's continue to example number 3. At this point, you should have copied it down. Now, we graphed this type of functions before. Do you guys remember when we graphed them? And what do they look like? Correct. If we go into decimals, we have f of x equals 1, f of x equals 1 over x minus 2. So that's what it looks like. So therefore, I need to be able to find the right-hand side limit and the left. So let's go and start. Let's just graph it. Do you guys remember how you find your horizontal asymptotes and your vertical asymptotes? This is back from chapter 2, 2.5 or 2.6. What determines your vertical asymptotes? Correct. Your denominator cannot be 0. So what values will make that 0? 2. So at 2, we have an asymptote because there's no such value. Do you guys remember your horizontal asymptote? Whenever the degree of the polynomial is bigger on the denominator, your horizontal asymptote is at 0. Y equal to 0. And where this is x equal to 2. And from here, I can graph it. Most of the time we usually have to plot a point. So if I plug in a 1, 1 minus 2 is negative 1. So it gives me 1 divided by negative 1 is negative 1. And which can just graph it. That's what we did back on chapter 2. And if I plug in a 3, 3 minus 2 is positive 1. 1 divided by 1 is 1. And I can graph it. So from the graph, we can find that the right-hand side limit, as x gets closer and closer to 2 from the right-hand side, what happens? As you get closer and closer, it gets bigger and bigger and bigger. So therefore, the limit of f of x as x approaches 2 from the right is going to be positive infinity, or just infinity. And the limit as x approaches 2 from the left of f of x is going to be negative infinity. Now, we can also do it algebraically. We can go into decimals, and now that we have the type 10, I can make a table. So I'm going to go insert a table, and instead of x1, I want to change it to just x. Instead of y1, I want to change it to f of x. And as I get closer and closer to, let's say, 2 from the left, will be 2.1, 2.1, and closer will be 2.01, and if I get closer, it'll be 2.001. If I get closer, it'll be 2.0001. Same thing that we did back on 12.1. If I get closer, 2.0001. Notice that it's getting closer and closer to infinity. Well, it's getting, we said that it's going to infinity. Not sure if it's getting any closer or further away. And we can include additional zeros, and as we get closer and closer to 2, notice that this is going to be very close to, well, we can say it's 2. And this will say undefined because it's not able to calculate so many zeros. But in this case, we can just get the idea. Or you can also do it on your graphing calculator. You can just do the table just like we've done before, or just like you guys did on section 12.1, where we did the table of values. Same concept. Next set of cutouts and example number 4. Go ahead and glue them together, write it down, and also type it into decimals. See if you remember what it's supposed to look like. Excellent. So at this point, you should have it glued and written example number 4. Definition of limits are infinity. If f of x is a function and L1 and L2 are real numbers, then the following statements are true. The limit as x approaches negative infinity is going to be a number. So this basically tells you that we can find the limit as x approaches negative infinity or positive infinity. And that says that notes the limits are infinity. Another thing that we need to start talking about is what happens as if we find 1 over x, or if we actually graph it, what happens towards the right and what happens towards the left. And the value of r can be any exponent. For our purposes today, let's start with just the basic f of x equals 1 over x. And let me just change the color. We know that that is the graph. Now, I'm going to add a table. So add a table, change it so it gives us values for the function. It'll be x. This will be f of x. And I'm going to type in a 1. So what happens if I type in a 2? Notice that it plots the points for you. It gets smaller. If I plug in a 3, and you can just press enter, plug in a 4, what happens to the f of x? 5, 6, 7, 8, 9, 10, and so on. And notice that it's plotting all the points for you. So what's happening to the y values as you plug in bigger numbers, and bigger numbers, and bigger numbers, and bigger numbers, and much bigger numbers? What's happening to the y value? So let me get to 100. See how fast this is. So as I get to 100, even though it seems like it's getting closer, it's actually touching 0. Is it touching 0? No. If you zoom in and continue zooming in, you start seeing a little gap. Do you guys see it? Correct. So it's getting closer and closer to 0. So close that we say that it's going to be reaching 0. So that's basically this means that as x approaches 0, whenever there's an x on the denominator, it's going to get so close that the limit will be 0. And same thing on the left-hand side, same concept. As the value of x gets bigger and bigger and bigger and bigger, it's going to get closer and closer to 0, so therefore the limit is going to be 0. So therefore, if I graph this on Desmos, we have 7 minus x to the power of 2. So notice that the exponent is not, it's still the same type of problem. So what's happening to the graph as it gets to positive infinity? What number is it reaching? And you guys can see it here. So you can either drag it or you can make a table. What is the y value going to become? It's going to get closer and closer to 7. So the limit as x approaches infinity of this is going to be 7. But why? Because this, as the x value gets bigger and bigger and bigger, this becomes, it's going to get closer and closer to 0. So therefore the limit as x approaches infinity is going to be 7. This becomes so small that the limit will be 0. So therefore that is 7. And let's just move on to example number 5, the last example for today. Well, there's 3 components, A, B, and C. Go and copy it down, and then once you have it ready, we'll start. Go and pause it. Excellent. So now we can actually graph it on Desmos, and usually I type in my f of x, and I usually place my fraction right away, and I go back and change it. So we have 4x plus 4 over x squared, 2x squared, plus 2x minus 1. So those type of graphs we've seen before. And what happens as x gets bigger and bigger and bigger? What is going to be the y value? And if you guys remember, we covered this type of graphs before. Back on section 2.6, we graph rational functions. And if you look on 2.6 of your notes, you should have this cut out. That we have 3 different components. If the value of the exponent, if the degree of the polynomial is bigger on the denominator, then it's going to be a horizontal asymptote at y equal to 0. If the degree of the polynomial is the same on the numerator and the denominator, in this case the degree is 1, then the coefficient 2 over 1 will be your horizontal asymptote. In this case will be 1 over 1, or in this case will be 3 over 2. And we'll come back to the last one in a few minutes. So therefore, to be able to calculate your limit as x approaches infinity, we're going to have to do it by hand. So therefore, I'm going to look for the biggest exponent. In this case, it's x squared. So I'm going to divide everything by x squared. I'm basically going to divide the numerator and the denominator by x squared. And I'm going to simplify it. So therefore, I'm going to have the limit as x approaches infinity. In this case, one of the x's cancels, so I end up with 4 over x plus nothing cancels, so I end up with 4 over x squared. Both x's cancel, so I end up with 2. One x cancels, so I end up with 2 over x. And nothing cancels, so I end up with 1 over x squared. So therefore, this approaches infinity, 0, this approaches 0, this approaches 0, and this approaches 0 according to our definition, to our previous cutout. So therefore, I'm going to end up with the limit as x, or this will be equals to 0 plus 0 over 2 plus 0 plus 0. So it'll be 0 over 2, which is 0. So therefore, the limit as x approaches infinity of 4x plus 4 over 2x squared plus 2x minus 1 is 0. And that is the method that we are going to use to find the limit of rational expressions. Let's try letter B. Go and write down, and then we can go through the same process. Excellent. So in this case, we're looking for the biggest exponent. But before we actually continue, in this case, notice that the degrees are the same on the numerator and denominator. So therefore, this will apply, where the coefficient will be your asymptote, and that will determine the limit. So notice that we turn everything down to chapter 2. I'm going to take the biggest exponent. I'm going to divide everything by x squared, x squared, x squared, x squared, x squared, x squared. And I'm going to simplify. So therefore, I'm going to end up with the limit as x approaches infinity. The x squares cancel, so I end up with 4. One of the x's cancels, so I end up with 3 over x. Nothing cancels, so I end up with 4 over x squared. Both x squares cancel. 1x cancel. And according to our previous calc, the limit, this will be 0, this will be 0. As x gets larger and larger, this will become 0, this will become 0. So therefore I end up with 4 over 2, which is 2. So therefore the limit as x approaches infinity of 4x squared minus 3x plus 4 over 2x squared plus 2x minus 1 is going to be 2. Just like we did on chapter 2. And for the last example, go and write it down. Go and pause it, and we'll continue once everybody's ready. Excellent. So, do you guys remember what happens when the exponent is the degree of the polynomial is bigger than the numerator? Correct. We go through the long division or synthetic division, and it will be a slanted diagonal, a slanted asymptote. So therefore, if we actually take the time to graph it on decimals, it's not going to look as nice as this because it's not factorable, the ones that I'm providing for you, or the one that we are working with. So in this case, this is 4x to the power of 3 minus 3x plus 4 over 2x squared plus 2. But notice that the same concept applies, that it's going to be a diagonal asymptote. But let's go and do it algebraically. I'm going to take the biggest exponent, simplify, and see what you get. And we can compare our answers afterwards. Go and pause it, and then we can talk about it. Excellent. So at this point, you divide by x to the third, x to the third, x to the third, x to the third, x to the third. So therefore, the limit as x approaches infinity, in this case, the x to the third cancels, so I end up with 4. 1x cancels, so I end up with negative 3 over x. Nothing cancels, so I end up with 4 over x to the third. In this case, x squared, correct? 2 x's cancel, so I end up with 2 over x, and nothing cancels, so 2x to the third power. So therefore, this becomes 0, this becomes 0, this will become 0, this becomes 0. So I end up with 4 over 0. Now, what happens if we have a 0 on the denominator? This, it seems that it should be undefined. But that's not true. Because according to a graph, as x approaches infinity, what are the y values? And we can actually type in just a quick table. Make this f of x. And plug in 1. What happens as the values get bigger and bigger and bigger and bigger and bigger? Or I make 200 or 500 or the numbers are getting larger and larger, correct? So therefore, according to this, it's infinity. But according to this, it's undefined. Why? So what is the difference and which is correct? Talk to your partners. I'll give you guys 30 seconds to discuss this. Ten more seconds. Yeah. So this is wrong because this is approaching zero, but it's not. This value is getting smaller and smaller and smaller. And if I take a value of 4 and I divide by a small number, it's getting bigger. Even if I go back and I type in a smaller number, it's getting bigger. So even though this is getting smaller and smaller and smaller, it's reaching zero, but it's not going to get to zero. So therefore, this number is going to get to infinity. So therefore, the limit as x approaches infinity of 4x to the third minus 3x plus 4 over 2x squared plus 2 is infinity. Just like we did back on chapter 2. So the homework is online. Have a great day and I'll see you guys next time.